Chapter 1: The Silence of the Vacuum, Atmospheric Expansion. Welcome to Synapse Daily.
We begin not with a bang, but with a terrifying, absolute silence.
Imagine 1968.
If you were standing on the earth, the world felt like it was spinning out of control.
Civil rights movements, a brutal war in Southeast Asia, and the existential dread of nuclear annihilation.
But if you were inside the Apollo 8 command module, the first human vessel to ever escape the gravitational well of our home planet, the world was just a fragile blue marble in a sea of ink. In that cabin, there is no air outside.
There is no help. There is only the hum of electronics. At the center of that hum sits the Apollo Guidance Computer, AGC. This machine was the bridge between human ambition and physical reality. We are used to computers being tools for entertainment or productivity.
But in 1968, for the first time in human history, a computer was the sole arbiter of life and death. If the AGC failed for 1 second during a burn, the astronauts wouldn't just miss the moon, they would vanish into a permanent orbit around the sun, becoming ghosts in a metal tomb. This was the birth of mission-critical computing. It was the first time we realized that to survive the stars, we had to build a mind that was faster, more precise, and more resilient than our own. This chapter of history is the hidden origin of every AI system we trust today, from the autopilot in a jet to the neural networks that manage our global economy.
Like this video if you learned something. Comment your thoughts below and subscribe for more fascinating stories. Chapter 2: The MIT Instrumentation Lab, Technical and Political Expansion. To build the AGC, NASA didn't go to a traditional computer company like IBM.
Those machines were giants, they were fragile behemoths that lived in air-conditioned basements.
Instead, they went to the MIT Instrumentation Lab, led by the visionary Charles Stark Draper. Draper understood something fundamental: space travel isn't about power, it's about information. You need to know where you are going, and how fast you're moving, every microsecond. The engineers at MIT, including Eldon Hall and Ray Sears, made a choice that was considered corporate heresy at the time. They bet the entire Apollo program on the integrated circuit, IC.
In the early 60s, ICs were a laboratory curiosity.
They were unreliable.
They were incredibly difficult to manufacture. The military, the primary buyer of electronics, preferred discrete components, individual transistors you could see and touch. But Hall saw the math. To get to the moon, you needed a computer that used less than 70 watts of power, roughly what a standard light bulb uses today.
You needed it to fit into a volume of 1 cubic foot. This forced a revolution. NASA didn't just use integrated circuits, they forced the industry to mature overnight.
They established the quality control standards that allow our modern microchips to work for decades without a glitch. This wasn't just a hardware victory, it was a logic victory. The AGC had to run a priority-based operating system. In the 1960s, this was science fiction.
Most computers ran one job at a time.
If the job got stuck, the computer sat there forever.
But the AGC was designed to be aware.
It had a night watchman, a hardware timer that checked if the software was looping.
If the computer became confused, it was programmed to kill lower priority tasks and restart only the essential programs. This is the ancestor of self-healing AI.
We were teaching machines how to prioritize survival.
Chapter 3: The Weavers of the Moon, Human and Manufacturing Expansion. Now, let us descend from the heights of MIT to the factory floors of Waltham, Massachusetts. This is where the abstract code of mathematicians met the physical world of needles and thread. The AGC's permanent memory wasn't stored on a disk or a drive. It was core rope memory.
Imagine thousands of tiny magnetic rings, each the size of a grain of salt. To store a copper wire had to be threaded through the center of the ring. To store a 0, the wire had to go around the outside. This work was so delicate that it was outsourced to the textile industry. Expert seamstresses, mostly women, spent weeks leaning over these ropes, weaving the software of the moon mission by hand. They were known as the LOLs, the little old ladies. Think about the sheer pressure. If a single wire was misplaced, if 10 became a 1, the spacecraft's navigation would be off by thousands of miles.
There was no undo button.
Once the wire was woven and the rope was potted in epoxy, the code was permanent.
It was literally hardwired. This created a unique bond between the programmers and the weavers.
Margaret Hamilton's team would produce the binary on paper tapes, and the weavers would translate that mathematics into physical copper geometry.
This is the most literal example of technology as a craft.
In our modern era of cloud computing, where data feels invisible and ethereal, it is grounding to remember that the first AI brains were woven with the same techniques used to make tapestries and sweaters. It was a human-machine symbiosis that bridged the industrial age and the digital age.
Chapter 4, The 1202 Alarm, the Psychological and Survival Expansion. The date is July 20, 1969. The lunar module Eagle is only 30,000 feet above the lunar surface. The engines are firing, the fuel is low, and the world is watching. Suddenly, a yellow light on the DSKY interface pierces the gloom of the cabin. 1202.
Neil Armstrong's voice is calm, but his heart rate is climbing.
Give us a reading on the 1202 program alarm. This was the moment the AGC earned its title as an intelligent partner. The computer was being overwhelmed.
A secondary radar system was flooding the CPU with 13,000 pulses per second of useless data.
The AGC's memory was full.
It was suffocating under the weight of information.
In a standard computer, this would have been a fatal exception.
The machine would have frozen, the guidance would have failed, and the Eagle would have crashed.
But the AGC was different.
Because of the priority scheduling designed by Hamilton and her team, the computer made a choice. It performed a soft restart. It dumped the useless radar data into the trash and focused 100% of its processing power on the landing throttle and the guidance sensors. It was the first time a machine displayed judgment. It determined that staying alive was more important than processing radar. In Houston, a 26-year-old controller named Jack Garman, who had a cheat sheet of alarm codes taped to his desk, saw the 1202. He knew that as long as the alarm didn't persist, the computer was recovering itself. He shouted, "Go!" That go was a vote of confidence in a machine's ability to think under pressure. The 1202 alarm proved that we could trust silicon to make executive decisions in real time.
This is the exact same logic used by modern AI to filter through millions of data points to find a single anomaly. The 1202 alarm wasn't a glitch, it was the birth of autonomous resilience. Chapter 5, The Silicon Diaspora, the Birth of the Valley. As the Apollo program began to wind down in the early 1970s, a strange phenomenon occurred. Thousands of the world's most elite engineers, men and women who had spent a decade solving the impossible problems of lunar navigation, found themselves looking for new missions. This was the Silicon Diaspora. These engineers didn't just take jobs, they took a culture. They moved from the high-pressure labs of MIT and NASA directly into the fledgling companies of Northern California. They brought with them the zero-fail mentality of the AGC.
At this time, a small company called Intel was just starting to experiment with the 4004 and 8008 processors.
The influence of the AGC was everywhere.
The manufacturing techniques perfected for the moon, wire bonding, hermetic sealing, and photolithography became the blueprint for the commercial semiconductor industry. But the most important export was the microprocessor concept itself. The AGC proved that you could have a general-purpose, programmable brain in a small package. Before this, computers were built for specific tasks.
Apollo proved that code could be flexible. When these engineers entered the civilian sector, they didn't just build faster calculators, they built the foundation for the personal computer. The AGC was the ancestor that died so that the modern microchip could live. Every time you open a laptop, you are using a descendant of the logic gates that once orbited the moon. Chapter 6, Fly-by-Wire, Intelligence in the Cockpit. The first place the AGC's civilian AI logic landed was in the sky. In the early 70s, NASA took a surplus Apollo guidance computer and literally bolted it into an F-8 Crusader jet. This was the birth of digital fly-by-wire. Before this, a pilot was physically connected to the wings by cables and hydraulics. If the pilot pulled the stick, the wings moved. But in the Apollo-inspired fly-by-wire system,
the pilot's movements were just suggestions to a computer. The computer would analyze the wind, the speed, and the altitude, and then decide how to move the wings to achieve the pilot's goals safely.
This is the exact definition of an intermediary AI.
It was a machine acting as a protective layer between human intent and a complex, dangerous machine. By the 1980s, this technology moved into civilian airliners like the Airbus A320. Today, when you fly on a commercial jet, you aren't really flying. You are telling a computer where you want to go, and the computer is using the same priority scheduling and error detection logic developed by Margaret Hamilton to ensure the plane stays in the air. This transition marks the moment when society began to delegate its physical safety to digital logic. We stopped trusting our muscles and started trusting the shadow pilot living in the silicon.
Chapter 7: The Kalman Filter, the Math of Perception. To understand modern AI perception, how a self-driving car sees a pedestrian or how your phone tracks your location, we have to look at a specific piece of math used by the AGC, the Kalman filter.
In space, data is noisy. Sensors are hit by radiation, they drift, they provide conflicting information. If the AGC had simply trusted its sensors, the astronauts would have been lost. Instead, the computer used a recursive algorithm to guess the truth. It looked at what the sensor said, compared it to what the physics of the spacecraft should be doing, and then found the most likely reality.
This is the hidden heartbeat of artificial intelligence. AI isn't about knowing everything perfectly, it's about estimating reality from messy data.
In the decades following 1968, the Kalman filter became the standard for every civilian navigation system.
It's in the GPS in your car. It's in the stabilizers of a drone.
It's even used in high-frequency trading on Wall Street to predict market movements. The AGC taught us how to teach a machine to perceive through the noise. It was the first step toward a computer having a sensory understanding of the physical world. Without this math, AI would be blind. With it, AI can navigate the chaos of the real world better than a human can.
Chapter 8: The DSKY and the Dawn of UI, Conversing with Machines. We cannot talk about the AGC without talking about the DSKY, the display and keyboard.
It was a blocky, gold-plated interface with a series of numeric buttons and a few status lights.
To a modern eye, it looks primitive. To a 1968 astronaut, it was a translator. For the first time, humans were interacting with a computer using a verb-noun syntax.
If an astronaut wanted to calculate a trajectory, they typed verb 34, terminate, or verb 06, display decimal.
This was the first time a machine didn't require you to be a programmer to use it.
It used a standardized, conversational language. This logic is the direct ancestor of the command line interfaces, CLI, of the 70s and the graphical user interfaces, GUI, of the 80s.
But more importantly, it was the start of human-computer interaction, HCI. The engineers realized that the computer had to talk back. When the 12:02 alarm flashed, the computer was communicating its internal state to the human. This feedback loop is what makes modern AI feel smart. Whether it's a chatbot or a voice assistant, the personality of the AI, the way it responds and guides the user, started with the blinking lights of the DSKY. We were moving away from commanding machines and toward partnering with them. Chapter 9: The Robustness Doctrine, the Ethics of Code. Finally, we must look at the robustness doctrine.
Margaret Hamilton and her team at MIT didn't just write code, they wrote defensive code. In 1968, the philosophy was, if a human makes a mistake, the machine should catch it. This was revolutionary. Most engineers at the time thought that if a user entered the wrong data, it was the user's fault if the computer crashed.
Hamilton disagreed.
She believed the machine should be a guardian. This philosophy is the foundation of AI safety and trustworthy AI.
Hamilton's code checked itself constantly.
It looked for illegal commands.
It monitored its own health.
When the Apollo technology moved into civilian life, into medical devices, nuclear power plant controls, and banking systems, it brought this guardian philosophy with it. We live in a world that works because the software is designed to be smarter than the mistakes we make. As we look toward the future of superintelligent AI, we are still asking the same questions Margaret Hamilton asked in 1968. How do we make sure the machine understands the mission?
How do we ensure it prioritizes the right thing when everything goes wrong?
The AGC wasn't just a technical triumph, it was a philosophical one. It set the standard for a world where machines aren't just powerful, they are responsible.
Chapter 10, The AI Winter and the Apollo Survival, The Bridge.
By the late 1970s and into the 80s, the initial euphoria of the space age hit a wall.
History calls this the AI winter.
The grand promises of machines that could think exactly like humans seemed to stall. Funding dried up, and the world grew skeptical.
However, the legacy of the Apollo guidance computer didn't disappear, it went underground.
While the world waited for human-like robots, the deterministic AI of the AGC was quietly taking over the infrastructure of civilization.
This was the era of expert systems. Engineers realized that if you couldn't make a machine think like a human, you could at least make it think like an Apollo engineer.
The logic of the AGC's priority scheduling was baked into the first global communication networks. When you sent an early email or a digital packet across the ARPANET, the precursor to the Internet, it was the AGC's executive logic that managed the traffic. The computer didn't need to be sentient, it just needed to be relentless. During this winter, the hardware continued to shrink. The legacy of NASA's miniaturization led to the Moore's Law explosion. We moved from thousands of transistors to billions. But even as the chips grew smaller, the ghost of the AGC remained in the architecture. We were still using interrupts, real-time clocks, and parity checks, all refined in the crucible of 1968. The AGC didn't die, it became the subconscious of the modern world. Chapter 11, From Heuristics to Neural Networks, The Evolution of Logic.
In the 1990s and 2000s, something shifted.
We moved from the rule-based logic of Margaret Hamilton, where every if this then that was handwritten, to learning-based logic.
This is where the civilian path diverged from the lunar path.
The AGC was the pinnacle of logic.
It followed rules perfectly.
But modern AI, like the large language models we use today, follows patterns.
Yet, the connection is deeper than it looks. Remember the Kalman filter from Chapter 7? That math was about probability. It was about a machine saying, I think the spacecraft is here with 99% certainty. Modern AI is essentially a Kalman filter on steroids.
When ChatGPT predicts the next word in a sentence, it is doing exactly what the AGC did when it predicted the next point in the moon's orbit. The civilian world took the probabilistic heart of the AGC and applied it to everything: speech recognition, facial identification, and medical diagnosis. We realized that the universe isn't just a set of rigid rules, it's a sea of data that needs to be filtered. The brain that once calculated a lunar trajectory was now calculating the shortest route for your Uber or the most likely song you'd want to hear on Spotify. The search for truth in noisy data, the core mission of 1968, remains the core mission of 2026.
Chapter 12, The Ethics of the Invisible Pilot, The Modern Dilemma.
As we near the present day, we face a new version of the 1202 alarm. In 1969, the 1202 alarm was a moment of trust. Human pilots had to trust that the machine knew what it was doing. Today, we face this every time an AI makes a decision we don't fully understand. The black box problem of modern AI is the ultimate evolution of the AGC. When the AGC decided to ignore the radar, the engineers knew why because they wrote the code. Today, with deep learning, we don't always know why an AI denies a loan or diagnoses a disease.
However, we still rely on the Hamiltonian doctrine of safety.
We are building guardrails, modern versions of the priority scheduler, to ensure that when an AI gets confused, it fails safely. The 1202 alarm taught us that a machine doesn't have to be perfect, it just has to be resilient.
We are currently in a race to build artificial general intelligence, AGI. Many fear it, but 1968 gives us a reason for hope. It shows us that when we integrate machines into our most dangerous endeavors, they don't necessarily replace us, they augment us. The AGC didn't land the Eagle alone, it gave Neil Armstrong the information he needed to land it. This augmented intelligence is the true civilian legacy of the Apollo program. It's not us versus them, it's us plus silicon. Chapter 13, Conclusion, The Loom of the Future.
We have traveled from the factory floors of Massachusetts, where women wove copper with needles, to the edge of the lunar horizon, and back down to the smartphones in our pockets. The story of the 1968 Apollo guidance computer is the story of humanity's first successful attempt to create a civilian brain.
It was the moment we realized that our own biological limits were not the end of our journey.
We could build something that lived outside of us, something made of sand and light that could carry our dreams where our bodies could not go.
Every time you interact with an AI today, you are touching a piece of that 1968 legacy.
You are speaking to a descendant of the DSKY. You are being protected by the ghost of Margaret Hamilton.
You are navigating through the noise using the math of the moon.
As we stand on the threshold of the next great leap, missions to Mars, the cure for cancer, the solving of climate change, we will need the AGC's spirit more than ever. We will need machines that can prioritize survival, machines that can filter out the garbage data of our chaotic world, and machines that we can trust with our lives.
The loom is still weaving. The wires are just invisible now. Thank you for joining us on this marathon journey through Synapse Daily. We've covered 50 years of silicon history today. If this story touched you, if it made you look at your computer a little differently, share it. Let the world know that the AI they use today was born among the stars in 1968. What will we weave next? Whatever it is, let's make sure it's as invincible as the heart of the Apollo. Stay curious. Stay connected. This is Synapse Daily. Signing off.